Check it out now, y'all.
nanoHUB-U, online instruction.
All right, so we're now going to solve the first problem of week 3 from homework. And the way to do this, we're talking about the Graphene ZA mode. And this mode is usually called a flexural mode. So if I take graphene, which is a 2D material, and I think about waves that would be going up and down like this and moving through the material in that direction, that's the ZA mode. So it's unique to 2D materials, and in graphene it's actually quite important. The first thing to do to solve part A of the problem is to calculate the number of modes or number of allowable states in K-space within a region of an area of K-space. So what we want to do is find the cutoff wave vector, and we'll call that KQ. And the reason we're using Q as a subscript here is that this is a quadratic dispersion branch. So that's what Q is going to stand for throughout this derivation. And so if we think about K-space, let's take it, looks like this. Remember, it's two-dimensional, so I have Kx and Ky. And I take a circle. It's not quite centered there. And what I want to do is I want to define an area of K-space with a radius KQ, and inside of that I want to fit all of the allowable modes. And the way to do that is to say, well, the area of K-space will be pi times KQ squared divided by the amount of K-space area that each mode occupies. And I think that we've established quite well at this point that that's going to be 2 pi divided by L squared. And so this is going to give us our number of allowable states. Well, the number of allowable states is a big number, and we want to express that in terms of density. So we're going to now use the concept of number of states per unit area. So we'll call that eta sub A, and that equals n divided by L squared. And so we go through this and we find that KQ, that's this K-space radius that fits all of the allowable states inside, will equal 4 pi times the density of states, of allowable states, raised to the 1/2 power. And so far that's really more or less what we've done typically in the class. The uniqueness comes in now when we start to say, well, this is a quadratic dispersion, so omega equals a constant times k squared. This is for that ZA mode specifically. And what we find, if we now want to define a cutoff frequency, so we'll say that omega sub q is a cutoff frequency. This will equal the constant times that maximum wave vector that we calculated before, and then we'll just go through and do a simple substitution, so that cutoff frequency equals 4 times the constant c that comes from the dispersion relation times pi times eta sub A. And so that's the big result for part A. So now for part B, we want to calculate the specific heat of this ZA mode. So we're looking for the specific heat of the ZA mode, and our usual expression using this Debye type approximation where we put an upper limit on the frequency looks like this. So we have an energy term, that's h bar omega, And then we have our derivative of the distribution function. In this case, it's the Bose-Einstein distribution function with respect to temperature, multiplied by our density of states. And again, I'm going to put that Q subscript on here just so that you can remember that it's a special density of states, which we haven't yet calculated, but we will. And I integrate over frequency space, but only up to the cutoff frequency. Now, we have to figure out what this density of states is supposed to look like. So the fundamental definition is 1 over L squared times the derivative of the number of allowable states with respect to frequency. And if we just do a simple calculation of that, what we're going to do is first of all use the chain rule and take the derivative of the number of states with respect to k, and then multiply that by the derivative of k with respect to omega, the inverse of which is normally what we've been using for group velocity. Well, it is the group velocity here, but we're going to actually have something different because we have quadratic dispersion here. Now that when we go through this, I'm just going to do some simple substitutions here from our result in part A. That's an L, and that d omega dk is 2 times c. That was the constant in the quadratic dispersion multiplied by k. And it turns out when you evaluate these things that we get a density of states that's 4 pi divided by c. So the density of states is constant, which is different than what we found for two-dimensional materials with linear dispersion from the Debye approximation. So that's a big, kind of important result that's unique to these quadratic modes. Although if you think about it a little bit, for electrons that have also a quadratic dispersion, you find the same thing, a constant density of states for a two-dimensional material. So what we'll do now is we'll plug this back into our expression for specific heat. Again, this is for the ZA mode. And I'm just going to write out all of the terms where we're doing that expansion of the temperature derivative of the distribution function. We've done that. We've shown that in lecture. It's also in the draft textbook. All right, it's a fairly complicated integral, but the term h bar omega over kt keeps showing up, and so we use that as a non-dimensional energy term. And then we make some further substitutions. We find that from our expression for the upper limit on the frequency, the cutoff frequency, we're going to turn that into a temperature. Do a few other substitutions here, and we're going to call this theta sub q. That's going to be our cutoff temperature. And x, which we use very commonly as that scaled energy. I'll write it explicitly here in a moment. So x is h bar omega over kBT. And the point of this is that, oh, I'm sorry, I put a squared term here. I got ahead of myself thinking of a different branch. But what we find is that here the definition of this kind of special Debye temperature is h bar times the cutoff frequency divided by Boltzmann's constant. What we find is that for this type of branch, the specific heat is linearly proportional to temperature, whereas when we had linear dispersion, that was a factor of 2. So I kind of, along the way, just sort of, I guess by rote, I put the factor of 2 there out of habit, but maybe it's nice that you could see that by crossing that out and putting a 1, that it's actually different and special. For this case of ZA modes, we have a linear temperature dependence. So the ZA modes are low frequency, and so what we find with graphene is that at very, very, very low temperatures, the ZA modes dominate the specific heat, and indeed we can even measure a linear temperature dependence. But then as temperature increases, the linear modes, those are the longitudinal acoustic and the transverse acoustic modes, they become populated, and so then we get to a T squared type of dependence when those modes start to dominate, those branches start to dominate the energy storage behavior. So you can actually witness these sorts of things, these different temperature dependencies in different ranges or regimes experimentally. So that's one of the really nice things about graphene, is that it's a wonderful model material system to look at the various effects of dimensionality and some of these more unusual vibrational modes. All right, that's it for problem 1.
Alright, this is problem number 2 of homework 3. So shown here is the specific heat of potassium for very low temperatures. So what we observe from this graph is that CV by T scales goes linearly with the square of the temperature. So CV by T is observed to be A plus BT square, where the values of A and B are given for potassium from the experimental measurements. So what this essentially means is that CV is equal to AT plus BT cube. So relating back to the expressions for specific heat that were derived in the lectures, clearly the linear temperature dependence should come from the electron specific heat, and the cubic temperature dependence that should come from the Debye model, because this is really at very low temperatures where the optical mode does not really contribute to the specific heat. So this part AT should be the electron specific heat, and this should be the phonon contribution, which at low temperatures goes as T cube. So this should be CVP. So E and P denote electron and phonon here respectively. So and we already derived the expressions for these specific heat. So the electron specific heat was derived in the lecture to be pi square KB square eta E by twice the Fermi energy, and the phonon specific heat under the Debye model was derived to be 234 eta A times KB by the cube of the Debye temperature. So eta E here is the electron density, and eta A here is the unit cell density, but in this case of potassium it's the same as the atom density. Right? So that's what this means. So this essentially gives you the, I forgot the T here. So this gives the y-intercept, and this is the slope of the graph, and this part is the slope. Now coming to part B of the problem. So we are required to calculate the Fermi energy of potassium, and we are given the conduction electron density in potassium. So we need the y-intercept part for this problem. So the y-intercept from the experimental measurement is 2.08 millijoule per mole per temperature per degree square. Now we need to be a little careful here because these are in units of energy per mole per degree square, but these specific heat expressions are volumetric specific heats. So we just need to convert this into units of energy per volume per degree square. So and that is easy because we know the atomic mass of potassium and the density of potassium is also given in the problem. So if we just do that units conversion, we get this is equal to 4.59 into 10 power minus 5 joule per cc per degree square. So now it's in volumetric units, and now we can compare it directly with the expressions that were derived in the lecture. So this is equal to pi square kb square eta e by 2EF. Now we know eta E. It's given to be 1.34 into 10 power 22 electrons per centimeter cube. So basically, solving this equation, we obtain that the Fermi energy of potassium is equal to 1.71 electron volt. One more thing to observe is that you can clearly see that the Fermi energy is much greater than the thermal energy at room temperature. So kBT at room temperature is approximately 25 milli-electron volt. So this was actually an assumption that was made in the derivation of the electron specific heat, and you can see that it actually holds true for this metal under consideration. And going on to part C of the problem. In this part, we are required to calculate the Debye temperature, and clearly we need to use the slope of the graph for calculating the Debye temperature. So slope of the graph is given by 2.57 millijoule per mole per centigrade per degree per 4. Now again we need to convert this to volumetric units, because these expressions are again for volumetric specific heat. So doing that units conversion, this is equal to 5.68 into 10 power minus 5 joule per cc degree per 4, and this is equal to the expression given here. So it's 234 eta A kb by the cube of the Debye temperature. So and the atomic density is given in the problem. So substituting that and solving for the Debye temperature, we obtain that the Debye temperature is 91.1 Kelvin. So yeah, that's about it for this problem. And what we essentially observe is that the temperature dependencies that we derived in the lecture are actually fairly correct, because experimentally we observe a very similar temperature dependence. So that's the neat thing about this problem. Thank you.
All right, for problem 3.3, what we're going to try to do here is to understand the effect of dimensionality on the result from kinetic theory, the kinetic theory that leads to thermal conductivity. So the general expression for heat flux, or a general expression for heat flux in a z direction, is minus the z component of velocity multiplied by the z component of the mean free path multiplied by the spatial derivative of specific internal energy in the z direction. And so we can do a little bit of manipulation of that, do some chain rule on the energy term, and the first two terms are the same. The chain rule on internal energy, we use temperature as the variable for that chain rule, and then of course this term is our specific heat, and this will equal then again the velocity in the z direction, that component, the mean free path, and now the specific heat multiplied by the temperature gradient in the z direction, and it's this thing out front that we call thermal conductivity. And normally it's expressed not in terms of directional components of velocity and mean free path, but rather in terms of the general speed and overall mean free path. So in one dimension, what we have, there's only one direction, so we find that the z component of velocity is the velocity, and the z component of mean free path is the mean free path, and therefore the heat flux is simply minus velocity, mean free path, specific heat, and temperature gradient. In 2D, we have a different case. We have to now really think about dimensionality. The z component of velocity is v times the cosine of theta, where theta is the angle made to the z-axis, whatever direction that particle is moving. And the same thing goes for the z component of mean free path. That's going to be the overall mean free path multiplied by cosine theta. So now what we're going to have to do is sort of average over the cosine theta. And so this Q, this heat flux, is going to equal minus CV times the overall velocity, the overall mean free path, the temperature gradient, and then this averaging we'll do at the end. That'll be 1 divided by pi, because we're going to look at just a half space in 2 dimensions. An integral from 0 to pi of the directional terms from the velocity and mean free path, so that they each had cosine, so this becomes cosine squared theta. And what we find is then, if we just do that simple integral evaluation, it's minus 1/2 specific heat times velocity times mean free path times the temperature gradient. And then from the course notes and from the companion book, we found for 3 dimensions that the heat flux in the z direction is minus 1/3 CV times velocity, mean free path, and temperature gradient. And what so at the end of the day, we find that thermal conductivity equals 1 divided by the dimensionality times the specific heat, the velocity, and the mean free path. That's the big result here. And of course this is specific to kinetic theory, which is probably the simplest in terms of deriving thermal conductivity, but it's very informative, at least to understand how dimensionality can affect the thermal conductivity. So that's it for this problem.
Alright, in the last problem we will calculate the specific heat of a diatomic chain and essentially try to understand the contribution of the optical and the acoustic phonon branch towards the specific heat of this diatomic chain. So what I have on the paper here is the schematic of the diatomic chain, which has been discussed previously in lectures and the homework. Here M1 and M2 denote the masses of the 2 atoms which form the bases. A is the lattice constant, which is the spacing between the 2 bases, and G is the spring constant. Now, it was shown previously in the lectures and the homework that such a diatomic chain of atoms results in the following dispersion relation, which I'm going to very roughly draw here. So on the x-axis I've got k, which is the wave vector. On the y-axis I've got omega. These are my Brillouin zone boundaries, pi by a, negative pi by a. And I have 2 phonon branches. The first one is the acoustic phonon branch, and the second one is the optical phonon branch. So at higher frequencies we observe optical phonon branch, and at lower frequencies it's the acoustic phonon branch. Now, while calculating the specific heat of this diatomic chain of atoms, two important approximations are have been very famously used in the past. The first is the Einstein approximation, and the second is the Debye approximation. So the Einstein approximation states that the optical phonon branch can be approximated as a single frequency dispersion given by omega E, wherein omega E is can be approximated as the average of the maximum and the minimum frequency in the optical phonon branch. So if we observe this optical phonon branch, the maximum frequency occurs at the center of the Brillouin zone, whereas the minimum frequencies occur at the end of the Brillouin zone. And if I take the average of the frequencies, essentially the maximum and the minimum frequencies, I'll observe a frequency which lies somewhere in between, and this frequency can be denoted as omega sub E, which is the Einstein frequency. The second approximation is the Debye approximation, which gives us a Debye frequency. Now the Debye approximation states that the acoustic phonon branch can be approximated by a linear dispersion relation. Which extends beyond the Brillouin zone to a Debye cutoff wave vector given by KD. So on the left hand side I have negative KD. This is the Debye approximation, and the slope of this linear dispersion relation is the group velocity. So basically the Debye approximation states that the Debye frequency is nothing but the product of the group velocity of the acoustic branch and the Debye cutoff wave vector KD. Similarly, the Einstein approximation states that the Einstein frequency is nothing but the average of the frequency, the optical frequency at, so I'll put a square bracket here, the optical frequency at k equals to 0, and the sum of the optical frequency at k equals to 0 and the optical frequency at k equals pi by a. So this is the maximum optical frequency, this is the minimum optical frequency, and this half here denotes the average. Now if you go back to the lecture notes as well as the companion text for this course, we have derived expressions for the optical and the acoustic phonon branches in this diatomic chain. So I'm going to use those expressions to calculate omega E and omega D. So omega sub E is half of, I'm going to reiterate the expression written on the top, the sum of omega optical at k equals to 0 plus the optical frequency at k equals to pi by a, and this is 1/2 multiplied by the square root of 2g upon mu plus the square root of 2g upon m1. Here mu is the reduced mass and it is given by 1 divided by 1 upon m1 plus 1 upon m2. So simplifying this further, this can be written as square root of g upon 2 multiplied by square root of m1 plus m2 plus square root of m2 upon square root of m1 m2. So this gives us the Einstein frequency. Now let's calculate the Debye frequency. The Debye frequency is given as the product of the group velocity, and this is essentially the group velocity at the center of the Brillouin zone, k equals to 0, multiplied by the Debye cutoff wave vector. Now I will separately explain the group velocity at the center of the Brillouin zone and the Debye cutoff wave vector. Now for one-dimensional material, the Debye cutoff wave vector is given as the product of pi multiplied by eta of A, where eta of A is the unit cell density. So in this case, this is pi multiplied by 1 upon A, which is equal to pi upon A. So that is the Debye cutoff wave vector. Also, if you refer the companion text as well as the lecture notes, the group velocity at the center of the Brillouin zone is given as A multiplied by G mu upon 2 m1 m2 multiplied by pi upon A. So taking both these expressions, omega d can be written as the product of A. I apologize, the group velocity is only this and not multiplied by this. I apologize for this error. So therefore the Debye frequency can be given as the product of the group velocity at the center of the Brillouin zone, which is given by G mu A multiplied by the square root of G mu upon 2 m1 m2 multiplied by the Debye cutoff wave vector, which is pi by A. And simplifying this further, this can be written as pi multiplied by the square root of G upon 2 multiplied by m1 plus m2. I'm going to highlight these two expressions because they are important in our problem. So this is the Debye frequency and this is the Einstein frequency. Now the part A of the problem wants us to find the ratio of the Einstein temperature and the Debye temperature. So what we are going to do next is we are going to try to relate the frequency to the temperature, which is essentially related by a very simple expression. So for calculating the Debye temperature, we can write this particular expression: h bar omega Debye frequency is equal to Kb, which is the Boltzmann constant, multiplied by the Debye temperature. Similarly, for the Einstein approximation, h bar Einstein frequency is equal to the Boltzmann constant multiplied by the Einstein temperature. And therefore, we get that the ratio of the Einstein and the Debye temperature is equal to the ratio of the Einstein and the Debye frequency. And that is given as 1 upon pi multiplied by square root of m1 upon m2 plus square root of m2 upon m1 plus square root of 1 plus m2 upon m1. So this expression is the answer to the part A of the problem. In the part A of the problem, we described the Einstein and the Debye approximations to the phonon dispersion for a diatomic chain, and we calculated quantities like the Einstein temperature and the Debye temperature, and eventually calculated the ratio of these temperatures, which is written here on top. In part B of the problem, we are going to basically find out the contribution of the acoustic and the phonon branches to the specific heat of the material and understand its variation with the temperature. A couple of things before I move forward. The temperature here is normalized by the Debye temperature, as you can see here on the top, and the specific heat is normalized by a factor of eta A Kb, which is the Dulong and Petit specific heat, which comes from classical formulations. Okay, now the specific heat of the acoustic branch is given by C sub V comma D, which is under the Debye approximation. D stands for the Debye approximation, and this is given by eta A Kb multiplied by T upon theta D, and this is multiplied by the integral 0 to theta D upon T x square e raised to x dx upon e raised to x minus 1 the whole square. Just a reminder, this expression is for the one-dimensional chain of atoms. Similarly, the contribution of the phonon branch to the specific heat under the Einstein approximation, which is written as C sub V comma E, is can be written as eta A kb multiplied by chi sub E the whole square e raised to chi sub E upon e raised to chi sub E minus 1 the whole square, where chi sub E is theta E upon T. So this expression is the optical phonon contribution to the specific heat. Now, plugging in some values here and finding out numerical answers to the question, we find that for these three normalized temperature, the normalized specific heat or the Debye specific heat is given by these numbers. So it's 0.328. For T by theta D equals to 0.1, it's 0.973, and it's 0.993. And we can see that as the temperature increases and as it goes beyond the Debye temperature, the specific heat, the Debye specific heat, approaches the Dulong and Petit limit of eta sub A K sub B. Okay. Now going on to the specific heat of the optical phonon branch under the Einstein approximation, we find that for, I'll take a specific case of M2 upon M1 equals to 2. Now for M2 upon M1 equals to 2, theta E upon theta D equals to 1.226. This comes from the above expression, this expression, okay? So therefore, from this particular expression, knowing that theta T upon theta D equals to 0.1, 1 and 2, which is from this part of the problem, we can write that chi sub E equals to 12.26, 1.226 and 0.613 respectively. And we require chi sub E to calculate the optical phonon branch contribution to the specific heat. Okay, so if I plug in these numbers, and I can populate this table with the following numbers. So the normalized Einstein specific heat at these temperatures is given by 0.0007, 0.884 and 0.969. So the subtlety here, which is really important to point out, is that we are calculating specific heat at temperatures which are normalized by the Debye temperature, but for calculating the Einstein specific heat, we need to use theta E by T instead of T by theta D, and that is where we are going to use the expression which we derived in the part A of the problem. Okay. So now with this table populated, in the last column, I'm going to calculate the percentage contribution of the acoustic phonon branch to the specific heat at these three temperatures. So the values that come out are the following. So it's 99.78%, 52.4% and 50.61%. So there are a lot of interesting things to note here from this table and from these calculations. The first one is that as the temperature increases and as it tends towards the Debye temperature and even beyond it, the Debye specific heat tends towards the Dulong and Petit specific heat, which is eta A kb. Also, note that at very low temperatures, the Einstein specific heat or the contribution of the optical phonon branch to the specific heat is very low. It's almost negligible at this low temperature of T upon theta D equals to 0.1. Now, this is because at high frequency, the optical mode is not populated at such low temperatures. Also, as you will notice here, as the temperature increases to Debye temperature and beyond that, the optical specific heat also tends towards the Dulong and Petit model. And therefore, we can note from the final column that at low temperatures, majority of the specific heat comes from the acoustic phonon branch, and at high temperature, towards the Debye at high temperatures, at and beyond Debye temperatures, there's an equal contribution from the acoustic and the optical phonon branch, which is denoted, which can be seen here by the percentages being around 50%. Now I'm going to very briefly describe to you a Mathematica CDF tool, which is available for your use. And this tool will really help us graphically understand the problem that we solved in the last two parts, which is essentially the contribution of the Debye and the Einstein specific heat to the total specific heat of a diatomic chain of atoms. So what I have here on my screen are two graphs, which are dynamic graphs, which change as the mass ratio changes through the slider on top. The top graph is the dispersion relation, which has the optical and the acoustic branch, and the bottom branch tells you the percentage contribution of the Debye and the Einstein specific heat to the total specific heat. I can play an animation here by clicking the plus button at the end of the slider, and by clicking on the play button, I can essentially dynamically change the mass ratio, and you will observe below that as a result of changing mass ratios, the dispersion relation changes, and accordingly the contribution of the Einstein and the Debye specific heat to the total specific heat changes. The graphics in this particular simulation may appear choppy because of a few processor intensive functions that we have used in these calculations. Nevertheless, a couple of things to note from this particular simulation is that the acoustic branch dominates the specific heat at low temperatures, as you can see from the blue plot in the bottom graph, and this particular contribution tends to 50% for very high temperatures beyond the Debye temperature. Again, for very low temperatures, the optical phonon branch contribution to the specific heat, which is given by the Einstein specific heat, is almost zero, and this particular contribution also tends to 50% for high temperatures way beyond Debye temperature. The second important thing to note in this particular simulation is that as the mass ratio increases, the Einstein frequency moves further from the Debye frequency, and hence the temperature at which the acoustic and the optical contributions become equal to 50%, that temperature increases with the increasing mass ratio. Thank you.